10 years ago, fusion energy had one unbreakable rule. If you want fusion to work, you build it huge. Bigger machines, bigger budgets, bigger timelines. That belief gave us reactors so massive they cover the area of 60 soccer fields. Projects so expensive and slow that most people stopped believing fusion would ever arrive. But then MIT asked a dangerous question. What if fusion doesn't need to be huge at all? What if the future of limitless clean energy isn't bigger, but smaller, faster, and radically stronger? Because inside a modest lab in Massachusetts, scientists just crossed a line many thought was decades away. A moment that could finally break fusion's infamous promise of 30 years away. This is the story of how MIT shrank fusion, why superpowerful magnets changed everything, and why the gamble on a compact reactor called SPARC could redefine global energy forever. And the gamble starts now. Fusion sounds simple when you say it fast. Take two light atoms, usually hydrogen, push them together until they fuse, and a tiny bit of mass turns into a massive amount of energy. That's how the sun works. So why is it so hard on Earth? Because the sun has a cheat code. Gravity. The sun is so enormous that its gravity squeezes fuel under insane pressure. On Earth, we don't have that luxury. So instead, we use heat, extreme heat. To make fusion happen, plasma must reach temperatures of around 100 million degrees Celsius. That's hotter than the core of the sun. At those temperatures, plasma can't touch anything. If it touches a wall, it cools instantly and the reaction dies. So engineers suspend it using magnetic fields, forming an invisible magnetic cage. This is where the old logic came from. The Lawson criterion says fusion depends on three things: temperature, density, confinement time. If confinement time is short, temperature and density must be pushed even higher. And historically, the easiest way to improve confinement time was simple. Make the machine bigger. Large tokamaks give plasma more room and more time to stay stable. That idea justified megaprojects like ITER, the International Fusion Reactor under construction in southern France. ITER is humanity's biggest fusion bet, and it's most expensive. But big machines come with big problems. Fusion didn't fail because scientists weren't smart. It stalled because progress was slow, expensive, and unforgiving. In the 1950s, early devices called Z-pinches tried to squeeze plasma using electric currents. They looked spectacular and failed spectacularly. The plasma twisted, kinked, and escaped. In the 1960s, the Soviet Union introduced the tokamak, a donut-shaped chamber with carefully shaped magnetic fields. Suddenly, confinement times improved. By the 1970s, optimism exploded. Many believed fusion power was just a few decades away. Then those decades passed. In the 1990s, fusion was still 30 years away. In the 2010s, same story. The joke became famous, but the joke hurt. Here's the real problem. Big machines iterate slowly. If a small experiment fails, you fix it and try again next month. If a multi-billion-dollar reactor fails, you wait years. Megaprojects move carefully, slowly, and cautiously. Every change requires committees, reviews, and approvals. Innovation crawls. Fusion got trapped in a loop. Bigger machines, longer timelines, higher costs. And that's when MIT asked a different question. Instead of asking, how big does a fusion reactor need to be? MIT asked, what if we make the magnets stronger instead? In fusion, magnets aren't decoration. They are the steering wheel. Stronger magnetic fields hold plasma tighter, improving confinement dramatically. In fact, confinement improves roughly with the fourth power of magnetic field strength. That means double the magnetic field up to 16 times better confinement. That's not a small improvement. That's a game changer. The problem? Traditional superconducting magnets hit a wall. They must be cooled to 4 Kelvin using liquid helium, and they max out around 11 to 12 Tesla. Going stronger simply wasn't practical, until a new material arrived. The breakthrough came from high-temperature superconductors, especially a material called REBCO, rare earth barium copper oxide. REBCO isn't a fragile wire. It's a tough superconducting tape that carries massive current, operates at higher temperatures, 20 Kelvin, can reach magnetic fields above 20 Tesla. MIT's Plasma Science and Fusion Center teamed up with a startup spin-off called Commonwealth Fusion Systems. Their idea was bold but simple: keep the tokamak design, shrink the reactor, crank up the magnetic field. Smaller machines mean faster construction, faster testing, faster learning. Fusion finally operating on modern engineering timelines. But theory isn't enough. They needed proof. September 5, 2021. Inside a lab in Cambridge, Massachusetts, engineers powered up a Rebco magnet coil they had spent years building. At these field strengths, the danger isn't just heat. It's force. Magnetic pressure tries to rip the coil apart like a giant invisible hand. If the magnet quenches, loses superconductivity, it heats rapidly and risks destruction. The team increased current step by step. Sensors watched everything. Then the number crossed a line. 20 Tesla. The magnet held. No quench. No failure. A record-breaking magnetic field for fusion-relevant superconductors. One MIT scientist later said it felt like the future shifting. And the world noticed. Within months, Commonwealth Fusion Systems raised over $1.8 billion in funding. Backers included Bill Gates, linked investors, Google-connected funds, major energy companies. Even skeptics admitted this wasn't hype. This was hardware, measured, proven, and it led directly to the most ambitious compact fusion reactor ever attempted. SPARC. SPARC is still a tokamak, but with a different philosophy. Its goal: the smallest possible machine capable of net energy gain. The reactor, about 3 meters tall, plasma radius of 1.85 meters, fits inside an industrial building. It uses 18 Rebco superconducting magnets, generating fields over 20 Tesla, roughly double ITER's. Target performance: fusion gain Q greater than 1. Design goal Q equals 10. For comparison, the UK's jet reactor reached Q is almost equal to 0.67. ITER aims for Q10 in the 2030s. SPARC aims to test net energy conditions this decade, and at a cost under $3 billion, mostly private. But compact doesn't mean easy. Heat exhaust, neutron damage, tritium fuel supply, and regulatory hurdles remain massive challenges. Still, even imperfect results would change everything. Fusion has always lived between elegant equations and stubborn hardware. For decades, the safest strategy was simple: build bigger, wait longer, hope harder. SPARC flips that logic. It bets that stronger magnets can deliver the same confinement in a machine that's smaller, faster, and testable now, not 30 years from now. The bet could fail, but it will fail fast, and that alone is revolutionary. If the magnetic cage holds, fusion stops being a promise and starts becoming progress. And if you want to stay ahead of the biggest energy breakthroughs shaping our future, backhand index pointing right, like this video. Backhand index pointing right, subscribe for weekly deep dives. Backhand index pointing right, comment below. Do you think fusion finally arrives this decade? Because the fusion age may not be coming. It may already be starting.